Okay, so here's the second half now. Okay, so let's talk about multi-factor studies. Sorry. Okay. All right, so what happens when we have more than two factors? Our design get a little more complicated. So this is just a factorial design where we have three or more categorical independent variables. So not blocking, not covariate, just three independent variables. So we're kind of going to mix the notation that we use for ANCOVA and 2A ANOVA because we're going to have a gamma because that's really like a C. It's like using A, B, and C, so the three factors. Factor A will be A, alpha, B will be beta, and C will be gamma. So we're going to represent C as a third factor rather than a covariate, so don't get confused there. It's still going to be a categorical factor. So we're going to be treating each as a full factorial design. So that means we have all the factors crossed. All three factors are going to be crossed. So we're going to have full factorial models. So if we have, let's say, a 2 by 2 by 2 design, so 2 levels of A, 2 levels of B, 2 levels of C, we're going to have 8 total experimental conditions. And that will be every crossing of A, B, and C together. So A1, B1, C1, A1, B1, C2, A1, B2, C1, A1, B2, C2, A2, B1, C1, A1, B1, C2, A2, B2, C1, A2, B2, C2. I should really write this down. It's a lot easier than trying to remember in my head. But basically, if I didn't do it correctly, it's every combination of A, B, and C in the design. So here's the full factorial model. So you'll see here we have U dot dot, again, the overall mean. We have the main effect of being in factor A, the main effect of being in factor B, the main effect of being in factor C, and then every two-way interaction effect. So alpha beta, alpha gamma, and beta gamma. And then we have the three-way interaction, alpha, beta, gamma. And the same kind of summation thing. So they all sum to 0, so that it's constant. And then, so sum of all the interaction terms, sum to 0 at each level, and blah, blah, blah. Okay, so it's going to be pretty similar to what we've been doing, without the covariate and everything. So just our regular factorial ANOVA. We just have more parameters, right? So we have more factors and more levels. So here's all the, and I'm not going to make you do all these and, find every single one. So find all the alpha, beta, gammas. I mean, it could, but that's mean. So you're going to basically, if you wanted to estimate them, you would use these formulas to get each of the parameters. Okay, so now design matrix. So we have a 2 by 3 by 2 factorial ANOVA. So let me go to Paint so I can draw it out for you. Okay, so it's a 2 by 3 by 2. Sorry, I'm drawing with my finger because I don't know where my... Let me try. I guess that's good enough. Okay. Okay, so 2 by 3 by 2 design. So we have 2 alphas, right? So we need to estimate only 1. So we need an alpha 1 to estimate. So we have 3 betas, so we have to estimate 2 betas. So we're going to estimate beta 1 and beta 2. And then we have 2 levels of C, so we need 1 gamma, right? So we need an alpha 1, a beta 1 and beta 2, and a gamma 1. Okay, so now we need all the interaction effects. So first we need the AB interactions, and I'm going to kind of write big and I'm going to erase it all and do something new. So, so how many alpha betas do we need? We need every pairwise combination of the alphas and the betas. So we need an alpha 1, beta 1, so an alpha beta 1, 1, and then we need an alpha beta 1, 2, because I didn't write that right. Just write it like this and cross it out because I don't want to find the eraser. Okay. All right, now that's the ABs. Now we need the ACs. So we need every pairwise combination of the alphas and the gammas. So there's only one, so that makes it easy. So it's alpha 1, gamma 1. So it's alpha, I should write it like actual, right? Alpha, gamma 1, 1. Okay, and then we need the BC interactions. Okay, so the BC interaction, we need every combination of the betas and the gammas. So that's beta, gamma, 1, 1, and beta, gamma, 1, 2. Sorry, 2, 1. Ooh. 2, 1, because there's beta 2, gamma 1. Okay, then we need the ABC interaction. So this, we actually use a combination of the main effects. We don't worry about what interaction effects we have now. We use every combination of the alpha beta gammas that we have. So there's only going to be 2 interaction terms that we're going to need, right? Alpha 1, beta 1, gamma 1. So alpha, beta, gamma 1, 1, 1. And then alpha 1, beta 2, gamma 1. So alpha, beta, gamma 1, 2, 1. So alpha, beta, gamma 1, 1, 1. And alpha, beta, gamma 1, 2, 1. Okay, so hopefully you wrote these down, because I'm going to need, hold on, let me open it. One. No. I guess I'll get a new picture. I don't need to save it. Okay, so here's a new picture. We need a design matrix. We need a little bigger. So if we want to remember what we had in our, here, right? So we had mu dot dot, right, which we'll always have. We had alpha 1, we had beta 1, and beta 2. I can't write very small, but that's beta. And gamma 1. Alpha, beta, 1, 1. Alpha, beta, 1, 2. Alpha, gamma, 1, 1. Beta, gamma, 1, 2. And beta, gamma, that's not right, not 1, 2. It's 1, 1. Beta, gamma, 2, 1. Alpha, beta, gamma, 1, 1, 1. And alpha, beta, gamma, 1, 2, 1. Okay, so I made one little mistake. All right. So now remember that each column, maybe to make it easier, we'll write these on top. So we have the mu dot dot, alpha 1, beta 1, run out of room, beta 2, gamma 1, alpha beta 1, 1, alpha beta 1, 2, alpha, sorry, no, I want beta, gamma 1, 1, beta, gamma 2, 1, beta, alpha gamma. Did I do alpha gamma? Maybe I forgot the alpha gamma. That's what over here is supposed to be alpha gamma. Put it over here. Oh, no, you'll be confused. All right, hold on. Okay, so let me go in order. I was trying to remember the order in which I did it. At least you could fast forward to this. Okay. Okay, so here I am at alpha beta 1, 1, alpha beta 1, 2, alpha gamma. Oh, dang it. Alpha, gamma, 1, 1. Okay, beta, gamma, 1, 1. Beta, gamma, 2, 1. Alpha, beta, gamma, 1, 1, 1. And look, I have room. Beta, gamma, 1, 2, 1. Okay. Okay, so there's 3 by 2, there's 12 treatment groups, right? So there's 1, 1, 1, 1, 1, 2, 1, 2, 1, 1, 2, 2, 1, 3, 1, 1, 3, 2. 2, 1, 1, 2, 1, 2, 2, 2, 1, 2, 2, 2, 2, 3, 1, 2, 3, 2, 1, 2, 3. Yeah, okay. All right, so now we know all the mu's are getting 1s. And you can pause me if I'm going too fast, but I'll go through this kind of quickly, but you can pause the senses. The alpha 1s, it's all going to be effect coding again. So 1 if you're in the group, -1 if you're not. Alpha, we're at the first subscript. So the first subscript, If we're at 1, we get a 1. So the first 6, 6. And then we have a negative 1, 2, 3, 4, 5, 6. Then for the betas, we have, for beta 1, it's a 1 if we're in group 1, negative 1 if we're in 3, and a 0 if we're in 2. So 1, 1, 0, 0, negative 1, negative 1, 1, 1, 0, 0, negative 1, negative 1. Beta 2, same thing, except for beta 2. 0, 0, 1, 1, negative 1, negative 1. 0, 0, 1, 1, negative 1, negative 1. Gamma 1, that's for C. So we have 1, negative 1, 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 1, negative 1. Kind of weird. Okay. So now we have alpha, beta, 1, 1, 1. So it's the same thing with the two-way interactions. We're going to multiply the two columns together. So we have alpha 1 and beta 1 that get multiplied together. So it's 1, 1, 0, 0, negative 1, negative 1, negative 1, negative 1, 0, 0, 1, 1. Alpha, beta 1, 2. So it's alpha 1, beta 2, 0, 0, 1, 1, negative 1, negative 1, 0, 0, negative 1, negative 1, positive 1, positive 1. Alpha, gamma 1, 1, alpha 1 times gamma 1. So 1, negative 1, 1, negative 1, 1, negative 1, negative 1, 1, negative 1, 1, negative 1, 1. Okay. Beta, gamma, beta, gamma. Okay, so beta times gamma, 1, negative 1, 0, 0, negative 1, positive 1, yes. Beta, gamma, okay, 1, trying to think where we're at, negative 1, 0, 0, negative 1, positive 1, okay. Beta 2, gamma 1, that is 0, 0, 1, negative 1, negative 1, positive 1, 0, 0, 1, negative 1, negative 1, positive 1. Now the alpha, beta, gammas, we multiply the alpha 1 times the beta 1 times the gamma 1. So we don't worry about any of the interaction effects of what their coding is. So it's the alpha 1 times the beta 1 times the gamma 1 to get alpha, beta, gamma, 1, 1, 1. So alpha, beta, gamma. So 1 times 1 times 1 is 1. 1, 1, negative 1 is negative 1. 1, 0, 1 is 0. 1, 0, negative 1 is 0. 1, negative 1, 1 is negative 1. 1, negative 1, negative 1 is 1. I don't even know if I'm in the right column anymore, but I'm going down the line, so whatever. Negative 1, 1, 1 is negative 1. Negative 1, 1, negative 1 is 1. 1, 0, 1 is 1. 1, 0, negative 1, 0, 1, negative 1 is 0. Negative 1, negative 1, 1 is 1. And negative 1, negative 1, negative 1 is negative 1. Okay. So alpha, beta, gamma. So alpha 1, beta 2, gamma 1. Alpha 1, beta 2, gamma 1. We have 0, a 0, a 1, 1, 1 is 1. 1, 1, negative 1 is 1. 1, negative 1, 1 is negative 1. 1, negative 1, negative 1 is 1. 1, 0. Okay, we got two zeros there. Negative 1, 1, 1 is negative 1. Negative 1, 1, negative 1 is positive 1. That's part of the 1. I don't know what happened to my finger. Negative 1, negative 1, 1 is 1. And negative 1, negative 1, negative 1 is negative 1. Okay, we did it. Oh, it wasn't too bad. Okay. All right, so we got through the full factorial ANOVA design matrix. So you can see everything kind of builds upon each other. So one thing that you'll notice when we're building this design matrix is that all the factors are built upon the lower factors, right? So all of the three-way interaction here, right, is built upon each of the main effects. Well, and it also has each of the two ways upon it. So that's going to be important when we get to our model building, is that there's a hierarchy within the model. And you can see that in the design matrix that you can't get this three-way interaction without having the parameters for each of the main effects. So, okay, but we'll get to that. So, slideshow from current slide. Let me do it the right way. All right, so now we're going to partition our Nova table. It's going to look the same as what we did before, but just have a lot more sums of squares. So you see we have the sum of squares A, sum of squares B, sum of squares C, sum of squares AB, sum of squares AC, sum of squares BC, sum of squares ABC. And we find the degrees of freedom the same way we did with lower factorial ANOVAs, so like a two-way. To get the interaction term, we multiplied the main effect degrees of freedom. The same thing here. So to get the AB degrees of freedom, we're going to multiply the degrees of freedom for A times the degrees of freedom for B. The AC degrees of freedom are A and C degrees of freedom. And then the ABC are the degrees of freedom of A times B times C. So they're all multiplied by each other to get it. Mean square built the same way, sums of squares divided by degrees of freedom. And the F statistic, these are all the divisor is the mean square error. Okay, so A over error, B over error, everything's over error. So nothing like that. And the same thing, all the sum squares equal the sum square total. All the degrees of freedom equal to NT minus 1. The total sample size we have minus 1. Okay, so really the complexities of this is just really the number of estimates you have and the number of things you have to look at. So we're going to be testing the main effects the same way. So all three of them, if we have a three-way ANOVA, are there going to be, if we have more than two, we're going to do two keys test. If we only have two, we're going to look at the two means and compare them and see which one's larger. So really no difference. We can also do the Scheffé, or if we want to do something like that. Interaction terms, same way, we're going to do plots. Now we just have the three-way interaction plot that we can also do. So we'll look at our F values and we just have a lot more to test. So I'm not going to show you every single one just to save time. I'm going to show you one main effect and then you'll see that the others follow, right? So the main effect in A, we'll be testing the mean square A over mean square E. And this is where, again, you see the numerator and denominator degrees of freedom are important because the numerator is the main effect of A and the denominator is the error, so that's where the 2 degrees of freedom come from. And we're testing to see if the means are equal, so B and C follow suit with that. So the two-way interaction, it's the same thing. You have the numerator and denominator degrees of freedom, and we're testing the two, testing to see if there is a differential relationship between the effects of A on the different levels of B or vice versa. And then the three-way interaction will have a similar F test, and we're just testing to see if there is that three-way interaction effect going on there. Okay, so really the most difficult part in the interpretation comes when you're looking at the three-way interaction of whether it's significant. I know I put one in your homework so you guys can kind of start thinking about it a few weeks ago. But I'm going to talk more about it this week. So when you interpret a three-way interaction, what you want to do is think of it as comparing two, or however many levels of that third variable you have, multiple sets of two-way interactions. So it's just like when I talked about a two-way interaction, you were thinking of how the main effect was now different at each of those levels of the other variable. Now we're looking at how is the two-way interaction different at each of the levels of a third variable. So you pick one variable to interpret across, and usually this is based on, what is you're most interested in. So if you're like, a lot of times we're looking at gender differences. So how do males, have their two-way interaction compared to females having their two-way interaction? So you can talk about those differences in that relationship. So kind of just depends on what perspective you want to put on it, because you could put the graph three different ways, either across A, across B, or across C. So the BC interaction across the levels of A, the AC interaction across the levels of B, or the AB interaction across the levels of C. So those would be the three. So it really just depends on what you want to interpret across that. That's how you pick. So to look at an example, we have a researcher that's interested in looking at the effects of gender, body fat, and smoking history. So it's 2 by 2 by 2. And they're looking at exercise tolerance on their stress test. So let's look at the ANOVA results. So what we see is that we have 3 main effects, right? Body fat, gender, smoking. We have two-way effects for body fat, gender, body fat, smoking, gender, and smoking. And we have 1 3-way interaction, body fat by gender by smoking. Okay. So we can look at the main effects, we can look at the 2 ways, and we can look at 3 ways. So we can test all, so forth. So our main effects and our 2 ways are interpreted the same way. Let's say, I know we don't have a significant 3-way, but if it was significant, how would we interpret it? So when we plot the 3-way interactions, we're looking at the variables across the 3rd level. So basically we're looking at multiple 2 ways. So it depends on how we want to interpret it. We compare the interaction plots across the levels 3rd. So let's say we wanted to do gender. So this is the 3-way interaction here. It's not significant, but you can see it's the same directional. But let's pretend it's significant, and let's pretend that any differences we found. So really, between males and females, we see that in the low-fat condition, that the light smoking is significantly better than the heavy smoking, but in the high-fat condition, there's no differences, okay? Because that's the nature of the interaction. It's not significant, so there really is no effect. But if it was significant, what we would say is that for females, there's a larger difference between the light and the heavy smoking at the low-fat condition, and in the high-fat condition, if we're saying that those either they're not significant or males flip, so it's actually that, no, that's going to be non-significant. Let's just pretend that the only difference is in the low-fat condition for the 2 genders, and that the high-fat is no different. So what that is saying, that there is more of an effect of smoking for women. So if you see the differential, the mean differential then between the females and the males, it's much larger. Of course, the scale isn't the same, so theoretically I should put them on the same scale to make them more interpretable. That would have been smart. But pretending we're looking at the difference. So there's about 8 points difference here, and there's 5 points difference for the males. So it's definitely a larger difference for the females. So what I see, if this was significant, is that smoking had a larger effect on women because there is a bigger difference in the low-fat group. So smoking in the low-fat condition had a larger effect for women than it did for men. And then smoking had no effect on both genders in the high-fat condition because there were no differences there for the 2 genders. So that's how I would write that interpretation. Now, if we're going to do the same thing, let's say now across fat level conditions, if we're looking at, this is the low-fat condition, you can see these lines are almost parallel. So you can see that goes a little lower here for the heavy smoking here in the low fat. That's kind of what we were seeing in that other graph. But assuming that it's parallel, so females, again, the low fat condition, females see a larger decline in the stress level test as compared to males, because if we're drawing a straight line, it would be here, so it's lower than what we would expect. So females, again, the smoking had a larger effect on these females in the low-fat condition as compared to the high-fat condition. So it looks like there's a crossover effect here, but there's non-significant mean differences. Or you can look at across smoking levels. So here's the light smoking condition, here's the heavy smoking condition. So if this was supposed to be parallel, it would go like this. So in the low fat, the males actually benefited more from the light smoking. It's like a reverse thing about it. It didn't. Instead of affecting the females more, males benefited more from that condition. And then if this was supposed to be parallel, then the males again had more benefit even in the low fat condition, even in the heavy smoking. Okay, so you can see that the interpretation of three-way is not straightforward. Okay, it's complex. So if you get something that has 4 factors, do you even want to see what a 4-way interaction looks like? And the answer is no. So typically when you're running these complex, you can put as many independent variables as you want in them, but you don't fit anything more than a 3-way interaction because there's no way you even want to interpret a 4-way or 5-way or 6-way interaction. So we fit our model more towards what we can actually use and answer, as opposed to what we can actually we can fit. So we can fit something with a 6-way interaction, but why would we want to look at a 6-way interaction? So we usually don't fit anything higher than a 3-way, at least in this ANOVA setting. So there's other models where we can put more higher interaction depending on how they are. So here's some examples of 3-way interaction effects. So here is some kind of braking torque or some kind of picture that I Googled. So we see there is not a large difference in the hex condition between the knurled and the smooth, but there is a larger difference in the round between the knurled and the smooth, between the staked and the spun. It's really hard to interpret that when there's weird words. So basically I would say there's no differences for the hex condition, but if we look at the knurled, there are larger differences than the smooth and the round. So we see effects of the barrel and whether it's staked or spun in the round condition as opposed to the hex. Okay, so here's another 3-way. So we have nurturing and exploitive, and here's at risk and control, women versus men. So if we look at the difference, I don't even know what this variable is. If we look at the difference between the control and the at risk, so the exploitive, we don't see any significant differences between the women or the at risk and the control in the nurturing condition for either of the genders. However, you see there is a decline for men and women in the control condition when it's exploitive, but when it's at risk, there's a much larger increase in the exploitive condition as compared to men. So while there are no gender effects in the nurturing condition between the control and at risk, the at-risk condition is much more detrimental for the women in the exploitive condition as compared to men in the exploitive condition when they're at risk. So there is not much difference between the males and the females in the control condition at the exploitive. But when they're at risk, women find much more detrimental results. So the mean gets a lot higher as compared to the men. Okay, so this is multiple days. So we have day 2, day 4, day 6. So these are different conditions. Then we have motivation, caffeine, and the placebo, none, jet lag, interrupted sleep, I guess no sleep, jet lagged or interrupted sleep. So if we look over the conditions by day 6, so it looks like caffeine and motivation are working. Caffeine's definitely on day 2. So at day 2, both caffeine and motivation are working, all right, to keep the person awake. I guess these must be outcomes. By day 4, they're not really motivated anymore, but caffeine's working. So caffeine seems to be working. Day 6, it's also working. Motivation, kind of plummets out as well. So we see that the motivation works for the interrupted and total condition at day 2, but not days 4 and day 6. where caffeine seems to work across all the conditions, across all the days. Okay, so once we get to these higher factor studies, you'll see that we're going to want to do some model fitting because we don't want to run all of the factors, right? So if we have a 4-factor ANOVA, we don't want to start with all 4 factors in there, at least in the hierarchy we want. So we want to include all 3-way interactions or lower, but what's also important when we have these higher order factors is that every time we include one in there, you'll notice we lose some degrees of freedom. So especially if we have multiple different levels of a variable, we're losing a lot of degrees of freedom. So depending upon our sample size, that could be cutting a lot, right, and reducing our error sum of squares. So we want to build what's called the most parsimonious ANOVA model. So all the parameters or all of the estimates that are both significant and necessary to the hierarchy is what we will create. So that was that hierarchy, right? So what does it mean to be necessary to the hierarchy? That means that all interaction terms must include all of the lower order nested effects. So if we have a 3-way interaction, we have to have all 2-way interactions that encompass that 3-way, plus all the main effects that encompass it. So if we have a 3-way interaction term, A, B, and C, we have to have the effects AB, AC, BC, A, B, and C all included in the model, even if they're not significant. So if we have a significant 3-way interaction term, all of those parameters must be nested or included in the model. If we have a 2-way interaction, that means we have to include all of the main effects that are umbrellaed under that. So basically, we have a hierarchy within the nested nature. So we start with the highest order term, and we do model fitting through backward elimination. And when we do this backward elimination procedure, you'll see we always remove one effect at a time. And we do it in such a way that we always remove the most non-significant effects. So the ones with the lowest F values, which will also be the highest P values, but ones with the lowest F values. And we only do one at a time because every time we remove an effect, where does it go? Right? It goes back into the error term. And so every time we add something to the error term and we add degrees of freedom, that means our sum of squares error is going to change. And that's also going to change all the F values from every other parameter that we have in our model. So we have to be careful. If we take out too many things in one time, that's going to change all of our effects and we could have missed something. So sometimes something could be close to being significant. And once we take something else out, it becomes significant because we've removed that other effect. And then we don't have to remove it anymore. Okay, so we start with the highest level and we look to see if it's significant. If it is not significant, we can remove it as long as it is not necessary to the hierarchy of the model. So as long as there's nothing above it in terms of level. So we have the 3 ways, and under the 2 ways, and then the main effects. So if we're looking at the 3-way, we have to keep these 2 in there. So if it's not significant and there's nothing above it, then we can take it out. Right? And then the 2 ways, when we're looking at that, as long as we've removed the 3 ways, we don't have to keep those in there. So we can take those out if we want to because there's nothing above it. So as long as there's no one looking above your head, you can take it out. Okay. So let's go back to our stress study. So we have the 3-way full factorial ANOVA, right? And so let's start with the 3-way interaction, right? Body fat, gender by smoking. Let's look at the p-value. It's non-significant. Okay, so theoretically, we look at all the 3 ways, but there's only one. So that is non-significant. So what we can do is go back and remove that effect and rerun the model. And you'll notice our p-values are all going to change. All right, so now we're at the 2-way effects. So there are 3 2-way effects. None of these are necessary to the model because we don't have anything above it, right? We don't have any 3 ways. So we want to look and see if any are non-significant. Well, there are 2 that are non-significant. So how do we pick which one to remove? We look to see which one has the smallest F statistic. So the smallest F statistic is 1.244 here, right? So that's gender and smoking. So this is the first one we're going to remove. So we're going to remove the gender and smoking, move one at a time. So we did that. So now we have 2 left, right? So both are eligible for removal. We don't have any 3 ways. One is non-significant. It has the smallest F statistic. There's only one. So 1.514. Let's remove that one. Boop. Okay, so body fat by smoking, 0.011. Okay, So that's significant. So we can keep it in. So now, before we move to the one ways, what you'll see is that because we have one ways, the main effects, you'll see we have body fat by smoking. What two main effects are we going to have to keep in the model no matter what? Right? We're going to have to keep in body fat and smoking. Okay, so it doesn't matter, they are significant, but even if they weren't, we would have to keep them in because they are necessary to the hierarchy. So you can only look at the ones. So since body fat and smoking are nested in the interaction, both are necessary. So the only one that we can look at is gender. Okay, I'm sorry. Okay, so gender. So we look at gender. I'm going to click on it. And you see the p-values. It's significant, so it stays in. Okay, if it was not significant, we can remove it. And if body fat and smoking were not significant, we'd have to keep them in anyway. Okay, so this is going to end up being our full final, what's called a parsimonious model. It is the model with the least amount of effects necessary to the hierarchy and the most significant effects. I think that's how I wanted to say it. Okay, so it's the one that has all the significant nested and non-nested lower order effects. Okay, so again, one at a time, referring to the F statistics, don't look at the p-values, look at the F statistics to see what's the lowest, okay? Because the p-values are determined a lot by the degrees of freedom. So we really want to look at the F statistic itself rather than the degrees of freedom. So always look at the F, not the p-values. Okay? So once you get the higher order models like four-way, you only start with three ways and then you move backwards from there. Okay, so it's kind of, we're going to do that an example. So you'll see in the post hoc procedure is the same. You can do Tukey, Chaffee, run contrast, interpret the interactions. So let's do that model fitting now in SPSS. Okay, this is kind of a slow process here. Okay, so here's the three-way design. So it's the stress.sav data set. That's the state stress. Okay, so here's the stress data set. So you have body fat, gender, smoking, and the stress outcome. And the first thing we're going to do is start with a full factorial model. So we're going to go to Analyze General Linear Model Univariate. I'm going fast, okay, because you can pause me. All right, so I'm going to put body fat, gender, and smoking as FIS factors, dependent variable as stress. We're going to start with the full factorial, so we'll go ahead and do that. And actually, sometimes it's easier. We're going to run it, but I'll show you how to. We can put in the full factorial. Let me just run it. There. Okay. So at this point, do not run any of like the post hoc procedures or anything because we want to minimize the output we have to look at when we're doing the model fitting. Okay. So if you're going to run do any of your tests for assumptions, do that before this, but don't make graphs or like do post hoc tests until you have the final model because it could change and then you just get all this output you have to mess through. Okay, so we know we're going to have to build it. So what I'm going to do is I will show you. So Analyze General Linear Model Univariate. If you go under Model and hit Build Terms, okay, I'm going to hit all the main effects. I'm just going to build the full factorial just to see what it looks like because then you can just remove them one at a time. Then it has this nice pull down, so you could do all two ways. So if you highlight all three and have all two ways in the pull down and click it over here, then it just automatically makes all the two ways and you don't have to remember which ones to include. So you can also do that for all three ways. So if you have like four factors, it'll do all the three-way interactions too. Okay, so this is the full factorial model. Again, I am just starting from scratch here. I'm pretending this is the first model I built just so you can see. Once I put all the factors in like this, it makes it a lot easier to go through and do the model building. Okay, so I'm starting with the third level, which is the three ways. That is non-significant, so I'm going to go remove it. So Analyze General Linear Model Univariate. I should still have it remembered. I'm going to remove that three-way and only include the main effects and the two-way. Hit OK. Then I'm going through my two ways here. Okay, again, I'm going fast because you can pause me and watch me over again. So we're going to get rid of the gender by smoking first. So analyze univariate. So gender by smoking was the first one. We just have to click it out of there. And then we're going to get rid of the body fat by gender. So analyze generally body fat by gender. Okay, and then we see all the main effects were significant. Body fat and gender had to stay in anyway. Body fat and smoking had to stay in. Gender was significant, so we would go out there. Now at this point, this is the model we're going to want to estimate and interpret. So we need to get post hocs for the main effects. Actually, we don't need post hocs. We just need means. So we can compare the differences. And we need a two-way body fat by smoking interaction. So graph. So we're going to go back to general linear model univariate. We'll get our estimated marginal means now that we know what those were. All right, we're going to get those for the main effects. I don't want that for all. Okay. We don't have to compare them because there's only two, but go ahead and get the marginal means. They're going to be the same as the descriptives if you'd rather do that. I just think it prints it out prettier when you do estimated marginal means. We want to do a plot, so we can do a plot, it's body fat by smoking. So body fat by smoking, add, doesn't matter which one because we have 2 by 2. Clue, boop, boop, and then it goes runs our output. Okay. All right, so I have included the interpretation. So again, we're moving once we've finished. So here is my write-up. So if we go to body fat, you see there is a significant effect of body fat, right? The F of 1 and 19 degrees of freedom is equal to 26.193, and the P is less than 0.001. If we go to the 2 body fat conditions, the stress level is significantly higher in the low fat condition as compared to the high fat condition. I probably should have put standard errors, but I just put means. All right, then we go to the main effect of gender. So gender was significant. There were significant gender differences. So 1 and 19 degrees of freedom again. F is equal to 19.068. P is less than 0.001. If we go to the gender means, you see that the males have significantly higher stress level tests means than the females. So males have higher means than the females. Then if we go to the smoking, so overall, males had higher exercise tolerance, is the way I wrote it. Smoking, F of 1 and 19 is equal to 7.600. P is equal to 0.013. So if we look at the smoking here, the means, there's significant mean differences. The light smokers had significantly higher levels of exercise tolerance than heavy smokers. Okay, so now we're looking at this. This is pretty clear what this is going to be once you look at the two-way interaction, right? So we saw that there was the two-way interaction. We're going to want to compare the effects of the main effect at the different levels. So we looked at light, heavy, right? What did we say in the main effect of smoking? Light smokers had significantly higher exercise tolerance than heavy smokers. Okay, now let's look at that in comparison to the fat condition. Light smokers had significantly higher stress level than heavy smokers in the low fat. Not true in the high fat. So that's where the nature of the interaction is that difference, while it averages to a significant difference, that difference is really in the 2 fat conditions. So in the low fat condition, smoking is much more detrimental. So like light smokers in the low fat condition had significantly higher stress levels than heavy smokers in the low fat condition. But in the high fat condition, those are individuals with high body fat. The effect of smoking was the same. So they had low stress levels independent of the level of smoking. I think I wrote something like that. low body fat, there are significant differences between light smokers and heavy smokers. Light smokers with low body fat had significantly higher exercise tolerance than heavy smokers with low body fat. In contrast, individuals with high body fat did not differ in their exercise tolerance based on their smoking levels. So both individuals that are light smokers and heavy smokers with high body fat have low exercise tolerance. Okay, so that is that. So I'm going to stop this video and make a third one, which is the scenic. So I want you to try this first. So we're going to do a little model building. We're going to do some recoding, which I will do at the beginning of that video. And then you're going to run a 3-way in ANOVA and try to find the best fitting model. Okay, I'll see you guys in